Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 38. And this problem asks us to draw the products of each of these reactions. So let's start with A. So A, we have this derived benzene reacting with SO3 and sulfuric acid. So what we need to do, just like in every other problem, is identify the directing effects of these substituents. So here we have a cyano group. So cyano is actually a meta-director because it's electron drawing. So we know we have two meta positions here and here. So we know that SO3 is going to add at the meta position. So we can draw the product of A, having our cyano group off the benzene ring on the top. And then in one of these meta positions, we can draw the SO3H that's going to be added on by this reaction mechanism. Now in B, what we have is an alcohol and nitro. The alcohol is going to be ortho and para-directing, while the nitro group in green is going to be meta-directing. However, in terms of strength, we know that because alcohol can actually donate into resonance into the benzene ring and donate a full carbanion charge in the benzene ring, the alcohol is going to have a much stronger directing effect than a nitro group, which is just pulling electron density away from through resonance. So we know that this effect is going to have the alcohol is going to have a much stronger effect than the nitro. So we know that we're going to have the substituent, which is the nitro group that's going to be added, actually occurring in our ortho and para position. However, this ortho position is non-reactive, as no chemistry is going to occur at this position because it's in between, it's meta between these two groups here. So when you have meta-derived products like here, or meta-derived starting materials like this, you have a one carbon spacer between your two substituents. There's no chemistry occurring in the carbon between these two large groups because of that steric bulk and interference that would occur. So you just have two carbons in which chemistry can occur at, one being the ortho position, one being the para position. So in B, we will have two isomers being formed, one the ortho, one the para, and we're actually also adding a nitro group here. So I'll draw the ortho product first, NO2, plus the isomer, being NO2, OH, and this one is going to actually be the para-derived. Now in C, so in C, similarly, we're having some sort of direction by two groups. So here we have this alcohol that's directing ortho and para. And then we have the methyl group that's directing ortho and para as well, because both of these are electron donating groups. But the difference is that the alcohol is donating through resonance and actually creating a full negative charge in your benzene ring, while your methyl group is just donating an electron cloud into your product to be formed, and that's not actually as strong as resonance. So the effects of the alcohol group is going to overweigh the effects of your methyl group. So what you're going to have is actually a product that is going to be directed through the alcohol, being one at the ortho position and one at the para position here. So for this one, C, we'll do C in green. Once again, we'll have two isomers, one the ortho and one the para, in respects to this alcohol because it's the stronger director. So I'll have the SO3H at the ortho position plus its isomer, at the para position with respect to the alcohol. And now we can move on to D. So in D, what do we have? Well, we have we're going to have Friedel-Crafts acylation occurring. And specifically, what's going to happen is that we have this alcohol group, or not alcohol actually, sorry, this so what we have here is actually, this is quite interesting. So we have, it seems like what we have here is some sort of ester group here. So if I were to redraw this so you can actually visualize this better. So we have an oxygen, then we have a carbon, and it seems like this carbon is double bonded to an oxygen like this, and then we have a chlorine group over here. So what we know about chlorine, well, your halides are ortho and para-directing, while your ester here is going to be actually ortho-directing as well. And sorry, I meant to say that your halides are going to be meta-directing or ortho-para opposing. That's what I meant to say. So your halides are going to be meta-directing. Why? Well, because they're electron withdrawing. And your ester is also, well, even though it is an ester, this oxygen can actually donate still resonance into the ring to form a full carb anion. So this is actually going to be an electron donating group because of that formation of a resonance charge and the ability to have a carb anion in the benzene ring. So in essence, what we're going to have is ortho and para-directing from this oxygen, but the para position is occupied here actually. So what's going to happen is that we have overlap of the directing effect from both these substituents. So we will attack the meta position in respects to the chlorine, or the ortho positions in respects to this ester here for this Friedel-Crafts alkylation. So what we can draw here now, you have your chlorine, then your ester, but this is a unique ester because this oxygen can still do resonance into the ring to make a full carb anion in your ring. And now, because of the internal plane of symmetry, we'll just arbitrarily choose one of these ortho positions and add the 2 carbons here. So 1, 2 for your Friedel-Crafts alkylation. So now let's move on to E. So E, what we have is an aldehyde and a carbon methyl group here. So we know aldehyde is electron withdrawing, so they are meta-directing. And we know that carbon are electron donating, so they are ortho and para-directing. So once again, just like in before, we have overlapping of both of these effects. So what we will see is that we are going to get isomeric products, one being the ortho and one being the para substituted products, with addition of this bromine group here. So we'll draw E here. So we'll have one bromine isomer at this position. Then we'll have another bromine isomer at the other directed position, which is this position here. And next we can move on to F. So what we have here is now another type of ester, but see now this ester is different from the ester in D, and this is why I actually drew out the starting material in D, just so we can visualize that this oxygen can actually have resonance into the ring to donate electron density within the ring. However, this ester is actually going to be electron withdrawing and pulling it away two of these two electronegative oxygen atoms, and there's no resonance that's going to donate any electron density into the ring. So there's only going to be electron withdrawing effects. So we know electron withdrawing groups are meta-directing. On the other side, we have this amine, and amine has those two electrons, or lone pair electrons, that can form resonance and a full carb anion into the ring. So it is going to be electron donating, and therefore ortho and para-directing. And once again, we have overlapping strengthening of the directing effect. So in this case, we have Friedel-Crafts acylation, and we are going to get the acyl group added at one of these ortho positions. Doesn't matter which one, because of the internal plane of symmetry in this molecule. So we can draw F. This is actually an amide. And here we have 2 carbons, so we have added a 2 carbon acyl group here. And now in G, let's see what G has in store for us. So G, we have 2 nitro groups, and both these nitro groups are electron withdrawing. So we know both are going to be meta-directing. So this top one is going to be meta-directing here and here, and the bottom one is going to be meta-directing here and here. But if you see, because there's actually an internal plane of symmetry, these 2 ortho groups are the same, or sorry, these 2 meta groups are the same, and these 2 meta groups are the same. So in essence, we're only going to get 2 products. Doesn't matter if you draw it here or here, or here or here, because they're both related to each other. So these 2 products would be the same as so would these 2 products. So you just have to draw your 2 products, your 2 isomers. One product for the meta position for the top nitro, one product for the meta position on the bottom nitro. So we'll do the top nitro, and I'll just say it's going to be this one. And then we'll do the bottom nitro. And I'll say it's this position here. So now, let's move on to H. So H, what we have is, now we have an ester on the right, we have an ester here, which is going to be meta-directing because it's electron withdrawing. And we have a methoxy group that's going to be electron donating, so it's going to be ortho and para. Para is occupied, so it's only the ortho position. So we once again have overlapping effects at these 2 ortho positions. Therefore, we're only going to get 1 product because they're identical, because of that internal plane of symmetry that we have in the molecule. So we'll draw the product H over here. And we're going to have that ortho halogenation at this carbon here. So now let's go on to the last 2 problems. So the last 2 problems, let's do with I. So I, we have a bromine group, which is going to be, once again, electron withdrawing, so it's going to be meta-directing. And we have this methoxy group, which is going to be, I'll do it in a different color, ortho and para-directing because it's electron donating. But now if you look at the strength of the donating group here, we actually notice that the methoxy group is a stronger director than the bromo group or any halogen. So methoxy, because bromine, it's actually just directing due to the electron pulling or inductive pull of electron density out of the benzene ring onto the electronegative bromine atom. But the methoxy group, it's directing through resonance, which actually puts a full carb anion charge in your benzene ring, making it a lot more nucleophilic for the electrophilic aromatic substitution. Therefore, the directing of this electron donating group, methoxy, is going to outweigh the electron withdrawing, meta directing of the bromine. So we're only interested in the direction of the stronger group, which is the methoxy. However, this ortho position is in between these two substituents, so we know that there's no chemistry that's going to occur between these two substituents, just like in B. So we only have these two isomers that are going to form. So this is I, so we're going to have bromine, methoxy. One of them is going to have the SO3H on one of the ortho positions, and the other isomer is going to be at the para position with respects to the methoxy group. Now, last but definitely not least is J. So in J, we have an electron withdrawing group and another electronegative group here, and then we actually have a nucleophile here. So remember, sodium is your spectator ion, and sulfur and oxygen have very similar chemistry, so you can think of them as the same atom. Sulfur and oxygen are interchangeable, so J is actually the only one in which we have nucleophilic aromatic substitution. So we know that we're going to actually replace this good leaving group with this nucleophile here. So we're actually going to go through an addition elimination step for J on this very electron poor benzene ring. And we're actually going to do a substitution reaction for this thiol group here, this ethyl group here, and kick off your good leaving group, fluorine.